Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers, and we will extend our discussion on magnetostrictive transducers for measurement of various physical parameters. So in this video we are going to discuss about the application of magnetostrictive transducer for measurement of strain. Okay, so before doing that, let us just review some basic concepts related to stress and strain, because these things will come in this discussion. So first, stress. So stress is actually a measure of when force or pressure is applied on a particular material, how that material responds to that in terms of its change in dimensions, that is length and volume, all that is called as stress, the response to force or pressure. That, okay, so it is a ratio. In simple terms, it is a ratio of the force applied to the cross sectional area of the material. Simple. Pressure or stress, that applied force by area. Okay, this is simply stress, and the units as the same units of pressure, Newton per meter square, and there are other units as well. Then we have strain, which is the response of the material to the applied stress or pressure or force. It is the deformation or change in dimensions of a material as a result of the applied stress. Okay, so as I said, the response of the material, the change in dimension of the material, it can happen through change in volume or change in length. In that way we can measure the changes that have happened in the material because of the applied stress. So there are two ways in which we can express this response, that is strain. First, in terms of length, which is called as longitudinal strain. Okay, this is called as longitudinal strain, which is basically change in length, how much length has changed, whether it is increase or decrease, whether it is compression or expansion that has happened in the material because of tensile stress or compressive stress, divided by the original length of the material. Okay, or we can express it in terms of volume, which is called as volumetric strain. Okay, because whenever stress is applied, whether it is tensile or compressive, expansion or compression happens. In case of expansion, volume, there is a decrease in volume or increase in volume because of the resulting compression and expansion. So here it is the change in volume divided by the original volume. So here is the thing. So whenever stress is applied, there can either be elongation of the material, which can lead to increase in length, and as a result of that, the corresponding decrease or in volume that happens, or when compression happens, it kind of inflates and its length decreases. Okay, in this case the length decreases, and in this case the length increases. So here is the change in length and the change in volume that has happened. So volumetric strain is the change in volume to the original volume. Longitudinal strain is the change in length to the original length. Okay, so this is the concept of stress and strain. And then another important law which forms the basis of the design of this magnetostrictive transducer, that is the Hooke's law, which generally states that for small deformations, for very small change in dimensions, change in length or volume or cross-sectional area, whatever, the stress and strain, they are proportional to each other. That is, the strain induced in the material is directly proportional to the applied stress. And the important thing here is that it is only applicable for very small deformations, and this range of small deformation is called as the elastic limit of the material. Okay, so for very small deformations, stress is directly proportional to strain. This is the relationship of Hooke's law, the mathematical representation of Hooke's law. So whenever there is a proportionality relationship, it is obvious that there will be a proportionality constant. So that is called as the modulus of elasticity. Okay, within the elastic limit it happens, so that's why this constant is called as modulus of elasticity. So if we see a general stress strain curve, this range, okay, this to this, where stress is directly proportional to strain, this region is the elastic limit. Okay, the elastic limit of the material. This is a general stress strain curve. Now, depending upon the nature of the material, the composition of the material, the stress strain curve can vary. There is no hard and fast rule that all the materials, they will have the same stress strain curve. So depending upon their nature, their stress strain curves will be different. So here I have taken a very general stress strain curve example. So within this elastic limit, this proportional range, stress is directly proportional to strain, or stress is equal to psi 0, where C is the modulus of elasticity. Now, as I said, strain can be expressed in two ways, in terms of change in length and change in volume. That's why there are two ways in which this constant modulus of elasticity can be expressed. First, modulus of elasticity of length, which is called as Young's modulus, and modulus of elasticity of volume. So this is for longitudinal strain, this is for volumetric strain. So that elasticity of volume, that is called as bulk modulus, and it has different values for different materials. You please check the material science and engineering playlist, where we have gone in detail about these things. Okay, there, if you want to have more information on this, you can check the material science and engineering playlist. So here are some of the values of the modulus of elasticity of length and volume, that is the Young's and bulk modulus for some materials. Okay, these are some of the values. Now, the choice of a particular engineering material for any purpose, for any design purpose, for sensors, transducers, or any components in any engineering design, it depends on some requirements which we want to have. So here, for this strain sensor, especially for strain sensor, the choice of the material will be such that it has a high elastic range. The proportionality range should be high. If it will be low, then that sensor will be useless. So this proportionality range should be high. It should be more. The area under this proportionality curve should be more for strain sensors. Okay, so this is the requirement. So this is stress strain relationship. Now, how we can utilize this principle and combine it with magnetostrictive effect to measure strain. So here the relationship is, if you want to calculate strain, strain is equal to stress by modulus of elasticity. So for this, we should know the modulus of elasticity of the material, that is Young's modulus or bulk modulus elasticity. So it depends whether we are using length as the measuring parameter or volume. Generally length is used, but volume can also be used, but length is easy to measure. So that, and stress. So this is constant, it will be given in the material specification, the sensor specification sheet. This value will be given, this will be known. Now we have to use the magnetostrictive sensor to measure stress, which will give us the value in terms of EMF. If you know, magnetostrictive sensor, it measures stress and gives an output in terms of voltage. So how it happens? Just let's have a quick review of that also. So we know magnetostrictive effect is the property that when a particular ferromagnetic magnetostrictive material is exposed to a fluctuating magnetic field, it responds to that with change in its dimensions, physical dimensions, that is change in length, all that. The reverse effect, that when mechanical force or pressure or physical force or pressure or stress is applied, that causes a change in its magnetic characteristics. This Villari effect or the reverse effect is utilized in magnetostrictive sensors for physical parameter measurement, because the input is a physical parameter, the output is a electrical parameter, which we want. We want to measure everything in terms of some electrical quantity, voltage or current. So this reverse effect is used. Stress, force, pressure is applied. That causes a change in the magnetic characteristics, especially permeability or relative permeability. That change in relative permeability, it causes a change in the magnetic flux density, because generally the magnetostrictive material is designed in the form of a solenoid or toroid. It can be an array or series of solenoids and toroids, or single solenoid toroid. So the magnetic flux density of a solenoid or toroid is given by this: mu 0 mu r n I. Mu 0 is absolute permeability, mu r is relative permeability, n is the number of turns of wire wound over that toroid or solenoid, and I is the current passed through it. Current is kept constant, number of turns of wire is constant, mu 0 absolute permeability is constant. So the only two things that are interrelated are the relative permeability, which depends on the applied stress or pressure or force or whatever you want to call it, the physical parameter, that causes a change in the magnetic flux density. The change in magnetic flux density causes a change in magnetic flux as per this relationship, because we know it is the dot product of the magnetic field vector and the area vector. Then as a result of that, as per Faraday's law of electromagnetic induction, an EMF is induced, which is given by this relationship. Now from this EMF we get a measure of the stress, okay, the stress applied on the material. Now as I said, we are aware from the specification sheet of the sensor of the modulus of elasticity, whether it is bulk modulus or Young's modulus, whatever it is, we know that. Stress we get in terms of EMF. So from that we can calculate strain and we get a direct output in terms of strain. Okay, this is the design principle. Now everything else is the same, the design, construction, everything stays the same. Only thing that is important here is that the material which is used in this magnetostrictive sensor, the design, that ferromagnetic material should have a high proportionality or elastic range. That is the only requirement. Okay, so there some fine tuning adjustments are done. So like I said, every sensor or every device that you use, it has a certain minimum level and maximum level. Okay, some minimum value below which it cannot detect any output, some maximum value, if we exceed that, the sensor will be damaged. So that will all be mentioned in the specification sheet. Whenever you pick a particular device, we go through the specification sheet, which clearly specifies what is the maximum input that you can give, what is the minimum input that you can give, the safe levels of operation, range of operation. So all that is taken into account. So depending upon the operational requirements, different types of sensors are used, depending upon what kind of material is used, what are its minimum and maximum levels of operation. So all that is taken into consideration. So let us try to understand the operation of magnetostrictive strain measurement from a three-dimensional perspective. As I said, the design principle is the same, where we have the ferromagnetic magnetostrictive material designed in the form of a solenoid or toroid placed in a platform with a platform that kind of channelizes the whole application of force or pressure or stress at the impact point towards the ferromagnetic material. So here, as the force is applied here because of anything, okay, as the force is applied, the entire pressure or stress is channelized through this at this point, and as a result, because of the choice of the material which kind of takes the stress, that has a high elastic limit. Okay, the proportionality range of stress and strain relationship, that area covered is high. As a result, when it undergoes, whether it is compressive or expansive type motion, whether there is increase or decrease in length or increase or decrease in volume, that causes the electrical signal that we get, the final electrical signal that we get as per the stress strain relationship through this. Okay, whether it is volumetric strain or longitudinal strain, bulk modulus or Young's modulus. So Young's modulus or bulk modulus, that is already known, okay, that we already know. This stress that is given through the EMF signal as per Faraday's law and magnetostrictive effect. This is given in terms of volt or current, that we convert it into appropriate units, Newton per meter square or Pascal or whatever units is there through the specification sheet. From that we calculate the strain through this relationship. Okay, sorry, this is the opposite, sorry, this is the opposite. It is stress by the modulus of elasticity. This is the relationship. This is known already, and this is calculated from the sensor in the form of voltage or current, that is translated into appropriate units. From that we get the strain measurement. Okay, so this is the basic principle, operating principle of magnetostrictive strain sensor. So this is the basic principle of magnetostrictive strain measurement with the help of the basic relationship between stress and strain under Hooke's law, the elastic range or the proportionality range, combined with magnetostrictive effect or reverse magnetostrictive effect, Villari effect, which we use to measure the strain induced in a material. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.